25 minutes, I'll warn you at 5 minutes.
Okay, I got to stop watch running here. Okay. Okay, well, let me begin by, can you hear me? Let me begin by thanking the organizers for inviting me to give this talk. I'm particularly proud to be speaking in this Strings conference because it also marks the inauguration of the International Center for Theoretical Sciences, which is a wonderful new addition to the TIFR family. And I'm absolutely confident it's going to do very well because of the tremendous international support it's received from the very outset from all of you. The title of my talk, Sunil already announced, is Constraints on Inflationary Correlators from Conformal Invariance. And I'll report on these 4 papers, the last of which is in preparation. These are with Ishan Mata, who's now off doing mathematics, Archasman Ghosh, who's a postdoc at the ICTS, Nilay Kundu, postdoc now at HRI, Ashish Shukla, who's my student, and Suvrat Raju, whom you all know is at the ICTS. 2 key references which underlie our work are the very important work done by Juan Maldacena, the paper in 2003 where he calculated the non-Gaussianity in slow roll models, and the paper with Pimentel. There are also many additional references in the subject. I can't do justice to them, but let me just flash a few here. There's a work of, sorry about this, Antoniadis and collaborators, Finn Larson, who's here, and collaborators, Kenderes, McFadden, other collaborators, Paolo Creminelli and collaborators, Kehagias, Rioto, Sham, Shiu and collaborators, and Zaldariaga and collaborators. It really is, a lot of people have made important contributions, Senatori, Walter Goldberger and collaborators, etc., Justin Curry and so on. I'm sorry about this. I'll start with an introduction, tell you about the general approach we'll adopt, and then apply it to specific correlators, end by discussing the general form of the word identities and some conclusions. As you all know, inflation is an attractive idea. It explains the approximate homogeneity and isotropy of the universe and also gives rise to small perturbations which can explain the fluctuations in the temperature seen in the CMB and also provide the seeds for structure formation. These perturbations arise due to the exponentially rapidly evolving universe during inflation. They are quantum effects involving gravity and thus clearly of interest in any study of quantum gravity. The 2-point correlator for scalar perturbations, which I'll define in a minute, has been observed through its effects on the CMB. Subsequent progress will hopefully lead to observations of non-Gaussianity, the 3-point function, etc. And my whole talk will in fact be focusing on the study of these higher point correlation functions. Here is a plot from the Planck experiment. You've probably seen it. On the y-axis is the 2-point function for the temperature, and on the x-axis is the multipole moment across as you go across the sky. The blue dots are data, the red curve is theory, which fits very well, and into the theory is an input of the 2-point scalar correlator. The form needed to explain this data agrees very well with what you would get out of inflation. Now during the approach we'll adopt is one based on symmetries. So let's try to begin by understanding what are the symmetries at hand. During inflation, the universe was approximately 4-dimensional de Sitter space whose symmetry group is SO1, 4. Here is a form of the metric in Poincaré-like coordinates. The parameter h, which determines the rate of exponential expansion, is the Hubble parameter. The question we will ask is, what constraints do the symmetries impose on correlation functions of the quantum perturbations which are produced? And our analysis will also include the small breakings of symmetry which arise because during inflation the universe is not exactly de Sitter space, there are corrections. Now let me just say that such a symmetry based analysis has the advantage of being robust and model independent, not tied to any particular model. And just to amplify on that, the basic idea in a large class of inflation models is to add an additional scalar field, the inflaton, with a slowly varying potential. Here I have sketched it. To the extent the potential is nearly constant, we have a constant positive vacuum energy density and de Sitter space, and then the slowly varying nature of the potential allows the inflaton to roll and ultimately for one to exit then the inflationary phase. So here is a class of models, the canonical slow roll models, where you have 2 derivative terms for gravity and the inflaton along with this slowly varying potential, but of course you could have higher derivative corrections as well, which I have schematically sketched here, suppressed by some cutoff scale lambda, and these would be important then if the Hubble scale was of order lambda. This could happen, for example, even in weakly coupled string theory, where the cutoff scale would be of order the string scale, if we had a string scenario where the Hubble scale is of order the string scale, which is then much less than m Planck, because say the string coupling is much less than 1. Now I should say that we don't have so far, to my knowledge at least, an explicit string model of this type, but I suspect this has more to do with the limitation of string theorists rather than the limitation of string theory. So I think we should certainly allow for this possibility, which is actually quite an attractive one. And now, given our poor understanding, as I was saying, of string theory, we don't have such a concrete model and much less compute the perturbations which would arise in such a scenario today, but the advantage of symmetry based considerations is that they will still continue to apply even in such a situation. So that sort of illustrates why this is useful to do. In fact, I hope as I can bring out, these considerations can really be quite powerful. So let's begin by understanding the symmetries a little more. Here's the metric again. SO1, 4 has 10 generators. Some of the symmetries are obvious in this choice of coordinates. There are 3 translations and 3 rotations because the spatial part is just flat. There's a scaling symmetry because you can shift t, the time, by a constant and compensate for that by rescaling the spatial coordinates. That makes up 7 generators. The remaining 3 symmetries are what are called special conformal transformations, more complicated, and there's a vector bi with indices I taking values over the spatial directions which parameterize these 3 symmetries. So that's what we begin with. Now the SO1, 4 symmetries of de Sitter 4 are the same as those of a 3-dimensional Euclidean CFT, which is why I'll refer to them as I go along as the conformal group. But I should hasten to add at the outset that I will not assume any form of the DS-CFT correspondence in this work. Rather, the observations relating symmetries of de Sitter and CFTs will only serve to organize our discussion of symmetries in the inflationary context. Now also, as I mentioned, during inflation these symmetries are not exact, but all the data we have so far is consistent with the breakings being small. These breakings are parameterized in terms of the slow roll parameters, epsilon, which is h dot, the rate of change of the Hubble constant in units of the Hubble constant, similarly a parameter which measures the second derivative of the Hubble constant, and this parameter I am calling epsilon 1, which is the rate at which the inflaton rolls in units of the Hubble constant. And so in particular we will take these to be small, but we will incorporate their effects. The wave function is a useful way to organize the discussion of symmetries, because once we understand the constraints imposed on the wave function, then the constraints on correlation functions automatically follow. And we will in particular be interested in the wave function at late time. So I have drawn schematically the expanding universe here. At some late time we take a spatial slice, chi denotes a generic perturbation on this late time slice, and we are interested in the probability amplitude for this quantum perturbation to arise. So the wave function will actually more correctly be a functional then of these perturbations. By late time I mean when the modes of interest have exited the horizon and stopped evolving. Using the translational symmetries we can label each mode by a co-moving wave number k. The physical momentum is k over a, and when that becomes less than the Hubble constant, these modes exit the horizon, and that's important because once they exit the horizon they stop evolving. So here is what happens to a massless scalar perturbation, and we will be interested in this talk in massless perturbations or nearly massless ones. If k square over a square becomes negligible, then the evolution becomes dominated by the friction term, and as a result this perturbation comes to rest and stops evolving, and that's a good time to then study the resulting wave function, because once they are frozen then they just stay frozen all the way till at a much later era they re-enter the horizon and start affecting causal physics. So we will be interested in this late time behavior then of these modes. Now taking a hint from the data which says that these fluctuations are nearly Gaussian, we can then expand the wave functional starting with a Gaussian term, which is this quadratic term, and adding corrections, cubic and so on. This is like doing a Taylor series expansion, except since we have a functional, the coefficients in the Taylor series expansion are actually functions here. So for now you see these quantities I am writing as within brackets Ox, Oy, etc. This is just a way of writing coefficient functions that then determine the wave function, or more correctly wave functional. But of course I have written them in a very suggestive way here as if they are correlation functions in some field theory, and the reason for this is the following: when we think about the symmetry constraints that will be imposed on the wave function, they will in turn of course lead to constraints on these coefficient functions, and so they will lead to symmetry constraints, and these constraints will turn out to be identical to Ward identities imposed by conformal invariance on corresponding correlation functions in a CFT. Okay, and in this way the study of constraints imposed by the conformal symmetries will be mapped to the study of constraints on correlation functions in a CFT. So this is the central idea behind the analysis. We'll map the problem of interest to one in a CFT, which is a more familiar setting for us to try and understand. And the breaking of conformal invariance will then give rise to corrections to these Ward identities, which is the analog of the Kalin-Zimanzik equations, where you get extra terms because coupling constant starts running and you get non-zero beta functions. Okay, let's understand that a little better. The wave function can be thought of as being obtained by starting with some initial state and propagating it forward using a path integral. The initial conditions we'll take are the Bunch-Davies initial conditions which preserve conformal invariance. Since we are dealing with a gravitational theory, there is a factor of m Planck square 1 over g Newton which is out in front of the action. We can then make everything dimensionless with appropriate factors of the Hubble constant. That brings out a factor of h square in front, leaving behind s tilde, which will then be dimensionless in units of the Hubble constant. Since gravity waves have not been observed, produced during inflation have not been observed as yet despite some recent excitement, we know that this prefactor m Planck square over h square is very big, of order 10 to the 12 or even bigger, and that means we can do this path integral in the semi-classical approximation, namely by solving the equations of motion subject to the boundary conditions. In the stringy context this means loop effects are unimportant, but alpha prime effects might be important, as I mentioned before. Okay, all of this is in analogy with ADS CFT. The wave function here is the analog of the partition function. The late time values of the perturbations are the analog of sources in the boundary field theory, and this prefactor m Planck square over h square is the analog of n or n square depending on what context we are dealing with, and we are here therefore in the context in the analogous context to the large n limit in ADS CFT. Okay, again all of this is will just help us organize our discussion. Now there is one important difference which will be important as we go along towards the end of the talk, which is in the inflation or cosmology case you have to compute expectation values by taking the mod square of the wave function as we normally do and then doing a further sum over all possibilities to obtain the expectation value. This is different from what we would do in ADS CFT given the partition function. This will be actually of some relevance as we go along. The perturbations of interest are spin 2 tensor perturbations and spin 0 scalar perturbations. The tensor perturbations are just gravity waves. The scalar perturbations arise from a mixing of the inflaton and the trace of the metric, fluctuations in the trace of the metric. So how do we obtain these Ward identities? I'll just sketch that out very briefly. Let's start with the ADM form of the metric with the lapse function n and the shift functions ni. We can then set n to 1 and ni to 0 going to what's called synchronous gauge. But the equations of motion of n and ni must still be imposed, and these lead to conditions ensuring that the wave function is invariant under residual gauge transformations which still preserve synchronous gauge. This is familiar, for example, from just going to Coulomb gauge in Maxwell theory. And in particular the n equation of motion leads to the wave function being invariant with respect to time reparameterizations where t goes to t plus epsilon, which is a function of x, the spatial coordinates alone. Similarly the ni equations lead to invariance with respect to spatial reparameterizations. And when you impose these conditions on the wave function, then it leads to conditions on these coefficient functions which are the analog of these ward identities of conformal invariance, which you get in a CFT. Okay, so that's what happens. And more generally, if you have a breaking because you are in an inflationary background, you still of course have this general structure of the constraints due to the n and ni equations, and they lead to then the correct identities which now incorporate the breaking of conformal symmetry. So that's the basic idea. I'll just illustrate it here for you. Let's say we are in de Sitter space. I write the metric again, including now fluctuations in the metric, which I have decomposed into a trace part zeta and a traceless part gamma hat. Here is the wave function. I've only written the quadratic term here. There will be additional corrections, and now I write the coefficient function suggestively as if it were a 2-point function of the stress energy tensor, because that's how this coefficient function will end up behaving under the symmetries. Since we are interested in the late time behavior of the wave function, the metric has frozen out, is no longer time dependent. If I now impose invariance with respect to time reparameterizations, what happens is the trace of the metric changes, because if I take t goes to t plus epsilon, that will clearly change the trace of the metric zeta, and that's the only change because gamma hat has frozen out and it's time independent. As a result, the conditions translate to the trace of the energy momentum tensor vanishing, because that's what appears along with zeta. More correctly, of course, what I mean is coefficient functions containing the trace vanish for all correlation functions. This is of course completely familiar to us from what happens in a CFT. If we now go to the inflationary context, there's something else. We have to incorporate the fact that there's an inflaton. It has its fluctuations, which I show as delta phi. So for example, there's a quadratic term now, including the fluctuations of the inflaton, and the coefficient function I call now in terms of a 2-point correlator for some operator O, because that's how it will behave. In fact, this operator will have, scalar operator will have dimension 3 nearly, and so we have this feature. But now let's ask what happens to the invariance and the time reparameterization. Besides zeta transforming, also delta phi transforms, because now phi bar, the background value of the inflaton which is rolling, changes, and when you incorporate that, the trace no longer vanishes, but the trace of the stress energy plus phi bar dot over h times this operator O vanishes. Okay, and this is also, again I mean this in coefficient functions, this is again analogous to what happens in a CFT perturbed by operators, where the beta function is now given by the rolling of the inflaton in units of the Hubble constant. Okay, so now moving to specific correlators, in fact this relation between the trace and the operator O provides a convenient way to compute coefficient functions of the trace to leading order in the slow roll approximation. For example, if you are interested in the 2-point function, we express it in terms of O with this now prefactor which is phi bar dot over h square, and then we can get away by computing this in the de Sitter limit, okay, because the leading dependence on slow roll parameters is already identified. This is the kind of strategy which was adopted to think about a particular correlation function in this paper, which involves 2 scalar perturbations and 1 metric perturbation. That's related to the coefficient function involving 2 O's and 1 Tij, and what we found was that, which can now be calculated in the exactly conformally invariant limit, and what we found was that this is completely fixed by conformal invariance, with O, as I said, corresponding to an operator of dimension 3 and Tij to a stress energy tensor in terms of how they transform. The resulting form is here. This is now the expectation value for the involving 2 scalars and 1 tensor perturbation. The functional form is given in terms of S, which is a detailed function involving the magnitudes of the 3 momenta, and the overall normalization is also fixed in terms of the power in the 2-point scalar in the 2-point scalar perturbation zeta and in the 2-point tensor perturbation. Okay, so this is completely fixed by conformal invariance as a very detailed result. If this could be observed in the sky or through cosmological observations, it would be a very direct check of a central assumption of at least a large class of inflationary models, namely that the universe was approximately conformally invariant when these perturbations arose. In fact, it's even more general. It would really test, regardless of inflation, whether the universe was approximately conformally invariant when the quantum perturbations originated. Now just for the experts, actually what I'm calling zeta is more correctly the gauge invariant Mukhanov-Sasaki variable, which is conserved outside the horizon. In the gauge I use delta phi equal to 0, it becomes the trace, which is why I'm calling it that. Also, it's not a surprise from the CFT point of view that a 3-point function would be fixed. Here actually for purposes of cosmology it's more useful to present this in momentum space as I'm doing, and it turns out that even the contact terms, which are actually important sometimes and have physical significance, do get fixed by the requirements of conformal invariance. Okay, so now this was a particular 3-point function just to illustrate, but observationally the most significant non-Gaussianity arises from the scalar 3-point function, and this was studied in this paper. In this case it turns out, even when you adopt this strategy and go over into these operators O, etc., the breaking of conformal invariance cannot be neglected even for the leading order answer. The resulting ward identities take a form like this. You have a differential operator acting on the 3-point function of interest, doesn't vanish now, but it's given by the 4-point function in the limit where one momentum goes to 0 with a prefactor, which is now this beta function I told you, the rate of rolling of the inflaton. This is what you get from scale transformations, and there's a similar ward identity you get for special conformal transformations where this differential operator now has a somewhat different form, and it's labeled by this vector b that specifies which conformal transformation you're talking about. Okay, the detailed form is not important, but the basic idea is that you get linear equations for the 3-point function determined by the 4-point function in a suitable limit. The general solution for this is a homogeneous term plus a inhomogeneous term. The inhomogeneous term is determined by the source, which is the 4-point function in a particular limit, which can now be just taken, calculated in the conformally invariant limit to leading order in the slow roll. And the homogeneous term is fixed from conformal invariance completely and corresponds to the 3-point function of a dimension 3 scalar. Okay, and so in this way the 3-point scalar perturbation correlator is then completely fixed by data you can obtain in the conformally invariant limit. Now we argued that in the slow roll approximation generically the inhomogeneous term will dominate over the homogeneous term, which arises from the self interactions of the inflaton. A consequence of that is that the resulting answer to leading order in slow roll is not unique, because as we all know in conformal field theory the 4-point function is not uniquely fixed by conformal invariance even in this limit. So we can't say something generically without recourse to a particular model just from symmetries for the form of the 3-point correlator in this case, but we can say something about the overall magnitude, because generically we can argue that the 4-point function will not vanish in the conformally invariant limit if nothing else. There is the identity block which will propagate here in between, or more physically the stress energy tensor. In the bulk that corresponds to the fact that you will always get a 4-point function for inflaton perturbations arising because of graviton exchange. So this will not vanish. As a result, the overall magnitude of the inhomogeneous term is of order the slow roll parameter phi dot over h, and this is the extent of the suppression in the slow roll approximation. And when you then work out what the resulting expectation value for the 3-point scalar correlator is, although the generically the functional form will be of course different, it corresponds to FNL, which is this parameter used to estimate non-Gaussianity in the cosmology literature. It corresponds roughly to FNL having a value then of order epsilon, this slow roll parameter h dot over h squared. And 2 minutes, okay, I'm almost done. Thus the non-Gaussianity will be suppressed by this amount. This is hard to observe in the CMB, but might be observed hopefully through galaxy surveys, or perhaps more promisingly through 21 centimeter physics. I should say that this is a firm prediction that if the observers pull off this miracle and can be sensitive to non-Gaussianity at this level, then they should definitely see something, because the fact that you should have non-Gaussianity at least at this level I think just arises from symmetry considerations. Okay, so I think actually as a prediction this is an even firmer prediction I would say than saying that you had supersymmetry at the LHC. So much goes into that, may or may not be true, but I think I would say only symmetries pretty much go into this. for saying what is the magnitude of the tensor perturbation, we really can't say much on general grounds. It might have been something Bicep could have observed, it could be much lower, whatever. But I think this is really a firm prediction. Actually, we could even get luckier, as was argued in this recent paper. It could be that particles which propagate in the bulk there are some particles with a mass of order the Hubble constant which actually have couplings bigger than the graviton. They might give rise to an even bigger value than for the non-Gaussianity. Or it could be that the scalar sector breaks conformal invariance in a bigger way. For example, in dBi inflation, that might enhance non-Gaussianity. But even if all that good luck doesn't happen, I think at this level we really should see non-Gaussianity. So I think this is at least something we can say with some confidence. I'll end now just in 2 minutes by telling you about the general Ward identities. You see this, it raises an interesting question. You see, we are trying to compute local correlation functions in a theory of quantum gravity with fluctuations in the metric. Of course, I presented them to you in momentum space, but really equivalently I could have given them to you in position space, conceptually at least. And such correlators make sense in a theory of quantum gravity only after we fix gauge. Now if we do fix the gauge though, and then we try to see how things transform under conformal transformations, then generically what will happen is that the transformations will lead to a change of gauge. So the conformal transformations must be accompanied by a compensating coordinate transformation that restores the gauge to arrive at the resulting Ward identities. And this was something of a puzzle in the cosmology literature, and we addressed it in this paper I flashed. And another way to say that is that you have to go to expectation values after summing over configurations given a wave function, and you have to fix gauge here, otherwise the path integral over matrix is not well defined. Anyway, once this is understood, the general Ward identities actually valid to all orders in the slow roll expansion can be written down as we are doing in this paper. This is the Ward identity coming from scaling transformations, which has the form sort of like what I showed for the 3-point function, relating an n-point function to an n+1 point function in the limit where one momentum goes to 0. These were already written down by Juan for the relating the 2 and the 3-point function, and are now called the Maldacena consistency conditions. There are analogous equations for the special conformal transformations which I think are new. Here the form of the transformation for the scalar perturbation, for example, is more complicated, involving a linear differential operator but also nonlinear terms because of this subtlety I mentioned. And then there are corresponding Ward identities for the tensor perturbations which are even more of a mess but really can be written down to all orders now in the slow roll expansion. Okay, so let me just end by saying that I think approximate conformal invariance is a very powerful constraint actually on the study of perturbations, non-Gaussianity in particular. Hopefully this non-Gaussianity will be observed in the future, and we will be able to test whether the early universe was approximately conformally invariant, which is a very deep and beautiful fact we would like to find out about the early universe. The methods I talked about I think can be extended to dBi inflation and other models as well, and perhaps these considerations can help also in formulating a more precise DS-CFT correspondence. In the -1 minute I'm going to shamelessly again plug for my home institution of the Tata Institute of Fundamental Research. We have in part of the family is the National Center for Radio Astronomy, which has built the giant meter wave radio telescope. That's the world's largest telescope today in the meter wavelength. We will have competition very soon, but today. And one of its design goals is to look at 21 centimeter physics, which, as I told you, is a very promising arena for discovering, actually perhaps I think the more promising arena to discover in the long run non-Gaussianity. Unfortunately, India is developing too fast, so the noise from increasing mobile telephony and power lines is a big problem. I don't know if we'll be able to overcome that, but let's hope so. Thank you.
Fernando? Oh, should be a volunteer.
Question, your expression for FNL proportional to epsilon, how did you get the 10 to the -2?
Oh, I did a very crude analysis. I just said, let's say delta and epsilon are the same order and ns is measured to be 0.8. It could be different. Yes. I was giving you a ballpark figure. So, you know, of course, maybe epsilon is much smaller and delta is much bigger and ns is 0.96 for that reason. But I think generically in a large class of models, you'll have both parameters comparable, and
That's
then
an argument for seeing R, for instance, and it hasn't happened.
well, all right, okay, it's true, all right. The real firm prediction is epsilon, of order epsilon, you're right. Epsilon could be much smaller, you're right.
So then how small can it be to be observable in the 21
in real life,
Yes.
I don't know, this 21 centimeter tomography and so on people talk about. I'm not really an expert, but they, you get three-dimensional information, as Nima was saying on Saturday, and maybe they can pull it off. I mean, it's obviously something. They're at order 1, as you know, today in the Planck experiment. So, yeah, I did put in that number just to.
Eva.
But at order epsilon is.
You'd very likely have to see R first if you're going.
Is that right?
I mean, at the 10 to the -3 level. I mean, that's going to happen before these things happen. So. Okay. Smaller than 10 to the -3 is good.
Okay.
Eva.
Okay, that's a fair point.
So I have a question. So the effective theory of inflation, people talk about reaching a threshold where their UV cutoff hits the phi dot squared scale of slow roll inflation, at which point they say they could, from that, sort of conclude that the inflationary mechanism is closer to slow roll than it is any of the alternatives. Do I understand correctly that that threshold is easier to reach than actually then going and measuring what you're talking about, although, of course, the details of that would be spectacular to see.
Say that again. So
well, I'm just saying you're sort of getting at whether or not it's closer to slow roll inflation than other forms of inflation when you talk about these symmetries, if I understand.
yeah,
correctly.
that's true. That's true.
And the effective theory of the perturbations can be used to try and address that by formulating the threshold where the UV cutoff of that low energy theory hits the scale of phi dot squared.
Yeah, that's true.
And so I think those guys argue that once you get there, you have an argument that the underlying mechanism you can really see that it should be slow roll. Maybe that's too indirect, and you want to hold out for these detailed measurements. But I'm just asking, am I right that it's easier to do the first thing than the second?
I see, and they would see that through a
Just through the
tilt in the.
constraints, improving constraints on the various FNLs.
I see. Okay. Okay. Yeah. Yeah. Yeah.
It might translate to that.
Yeah. Okay. Okay. Yeah.
I mean, that allows for smaller corrections to slow roll, higher dimension operators that are not really infecting the mechanism, but maybe a little larger than what you're talking about.
Okay. Okay. Maybe they would see it that way. I mean, I did assume here that we have a small breaking. And if we allow, I mean, this approach is slightly complementary to the effective theory because we include all derivatives, but we assume conformal invariance is closely respected. And
yeah, this is not a criticism.
No, I understand. Observationally, I'm not really sure. Maybe you're more sensitive to CS -1 related effects in the non-Gaussianity, and you can tell that way whether it is slow roll or not. But even assuming it's slow roll, how far do you have to go for the non-Gaussianity? I think generically is of order epsilon. So.
Okay, I don't see any more questions, so let's thank Sandip again.